Welcome back to BSpice. In this session, we'll continue with metering system BSpice member question and answer session, part 2. So in part 1, we covered two questions actually. If you are a first time viewer, you can watch and get benefited. So this is the part 2. In part 2, we'll focus on density correction for custody transfer. Okay. So there are three questions as far as this density correction. This was sent by one of our member, so that's why we are supporting him. Okay, so yeah. So now the third A question, 3A. What is the minimum required density accuracy for custody transfer metering skid as per ADNOC standard? Okay, friend, ADNOC standard, of course, it's not publicly available. You can also refer if you are, already have the copy of that. But as per the industrial standard, in line with of course, aligned with ADNOC and API standard. Okay. Typically, it required a density accuracy of 0.0001 gram per cubic centimeter. Okay. So that is the one item I want to put forth. Okay. So this is one of the thing, and repeatability of 0.0005 grams per cubic centimeter. Grams per cubic centimeter for custody transfer application. So you got it, friends. So this is the one. Okay. So here one point I want to also inform you. These values are consistent with the performance of high precision instruments like micro motion compact density meter, right? So which are widely used in ADNOC, right? Yes. So you can go with this option, friend. Okay. So density plus or minus 0.001 G per cc and repeatability 0.00005 0.005 grams per cubic centimeter. Okay, good to go. Right, the first question is answered. Then second, 3B. Implementation of density correction in flow meters. That is the second question. How is the density correction typically implemented in flow computer? Sorry, yeah, flow computer, right? Okay, answer. Density correction is typically implemented in flow computer in this like this, friends. So like this means real-time input from a density meter. Real-time input. There could be a Coriolis or vibrating fork type. So the flow meter uses this input to convert the volume flow into mass flow, apply temperature and pressure compensation, and calculate the standard volume or mass for custody transfer. So this is how we do actually. We need to get the real time input from a density meter. Then the flow computer uses this input to convert the volume flow into mass and apply temperature and pressure compensation and calculate the standard volume. Okay. Then, this density value is integrated into the API table or custom algorithm within the flow computer for accurate reporting and ticketing. This is additional info. So this is how we do the density correction in flow meter. Okay. You got it, friends? Oh, friend. Okay. Then third question, 3C actually. Is only a pulse input from density allowed? So basically, your question is only pulse input from density allowed for calculation? The answer is no, actually. No, pulse input alone is not sufficient for density correction. This is not good enough. So because, analog or digital continuous input, whether it's a 420 milliamps, Modbus or HAL, is required to provide real-time density values. That is why. Okay. Then the other reason is pulse signal are typically used for flow rate or totalized function, not for density. Okay. And of course, ADNOC and API standard require continuous density measurement for accurate mass flow and standard volume calculation. So your third C also answered. Okay, I hope you also agree. Okay, right. Now I go into the fourth question, which this question is about prover constants in SCADA. Okay, so the question, which prover parameter are required to be entered in SCADA. Okay. So before answering the question, friends, I want to inform you. Now, as you know, in a custody transfer metering system, right? The SCADA system must be configured with specific prover parameters, isn't it? What for? To ensure accurate and traceable meter proving, isn't it? So these parameters are essential for validating the flow meter performance and ensuring the compliance with APMS. That is very important. API MPMS chapter 4, which I already talked in one of our session. API MPMS chapter 4, and of course ADNOC standards also. Okay. So the answer is like this. Which prover parameters are required to be entered in SCADA? Okay. One is the prover volume. This is calibrated base volume. Prover volume. The certified volume of the prover barrel or small volume prover, whatever is that. So that volume we need to, what do you call, needed actually. So this must be traceable to national standards. Okay. That one also we have to keep it in mind. Then prover temperature and pressure. So this is also need to be entered. So why? This is used to correct the prover volumes to standard conditions. Also to ensure accurate volume comparison with flow meter. So prover temperature and pressure needed. Then also the detector switch position. You would have seen in our video the detector position and all we have covered, right? Yes. So detector position switches also, detector switch position also we need to enter, meaning the start stop position for the prover run we need to enter. Okay. Then also the prover runtime, basically runtime in the sense time taken for the prover sphere or piston to travel between the detector. Okay, right? So this also we need to enter because this is used to calculate the flow rate and meter factor. So meter factor, in fact, I already talked, right? So if you have any doubt, you can also watch that video, meter factor, right? Then also number of passes. Number of passes in the sense that typically 5 consecutive passes are required. So SCADA system will average these to determine the meter factor. Okay. And finally, the meter factor. So the ratio of prover volume to the indicated meter volume. So this is the meter factor. So this is stored and applied in the flow computer for corrected flow calculations. Okay. And flow rate during proving. Right. So this is also we need to add. And also the prover type and configuration. So prover type means whether it's a bidirectional or what do you call small volume prover, all these. Okay. Then prover calibration certificate data. So that is also we need to yes enter. So this all your answers, friends. Which prover parameters are required? These are all the parameters. Now we go into question 5 actually. So the question 5 is related to again switching over philosophy of metering system. Okay, maybe I want to also update you, just step back a bit. Sorry, I forgot to. See, these are the mandatory, okay, but there are also some optional items like, viscosity, density of the product, ambient and product temperature. All these we can also add on as an optional, okay. So now coming back to question 5. So this is on the switching over philosophy of the metering system. So what is the question? What is the recommended logic for automatic or manual switching between metering skid line during maintenance or stream proving? Okay. So, okay. Friends, the switchover philosophy between metering system in custody transfer or whether physical metering is very critical. What for? To ensure the uninterrupted operation, accurate measurement and safe maintenance, right? So here, we have like uh, the two aspects, friends, actually. Okay. One is automatic logic, automatic switching logic. So this is actually we deploy or we employ this automated logic, switching logic during stream proving, meter failure and schedule maintenance. Okay. Then how the logic flow? First, the trigger condition detected, meaning proving request initiated, alarm fault on active meter indicates, then schedule maintenance flag. So this is the trigger condition. Then check standby stream availability. So standby stream availability means confirm the standby meter is healthy and calibrated, and confirm the valves and instruments are ready. So that is check standby stream availability. Then initiate switchover. Okay. So initiate switchover in the sense close inlet and outlet valves of the active stream and open inlet and outlet of the standby stream. Okay. Then update flow computer and SCADA with the new active stream. So we have to do this switchover. Okay. Then log event, that is also this is how first trigger condition, check standby stream, initiate switchover, then log event. Log event means the timestamp, all these. Okay. Then notify the operator, SCADA alert or HMI message. This is the, the logic basically. So to answer your question, there are two ways. One is the automated switching logic, other is manual, which I will discuss in the next slide. Okay. So automated switching logic, these are the scenarios. I'll go into the manual switching logic. So this manual switching logic is used during whenever, when operator intervention is required or automatic logic is overdone for testing or troubleshooting. So what are all the steps involved in this? See, first we need to, the operator select the standby stream via HMI SCADA, then system check the interlock and readiness, and operator confirm the switch and system execute the valve sequencing and update the flow computer. So this is about the, philosophy, friends. Okay. So, yeah, in fact, I have done with this. But before that, I also want to give you some safety and interlock during this switchover philosophy. Friend, no two stream active simultaneously, okay, unless designed for parallel operation. So interlocks to prevent switching during prover or calibration, and fail-safe logic in case of valve or instrument failure, and alarm generation for unsuccessful switch attempt. So these safety and interlock consideration we need to focus. Okay. Right. So that's all I have for this session. So I have covered totally 5 questions. So 6, 7, 8, 3 more questions are there that I will cover in the next video. Take care. Bye-bye.